स्वतंत्रता के अमृत महोत्सव के उपलक्ष्य में मध्य प्रदेश विज्ञान सम्मेलन एवं प्रदर्शनी 2021 में आप सभी का स्वागत है। मध्य प्रदेश विज्ञान सम्मेलन एवं प्रदर्शनी 2021 का आयोजन 22 से 25 दिसंबर 2021 तक भारतीय प्रौद्योगिकी संस्थान इंदौर में हो रहा है। इस सम्मेलन का मुख्य उद्देश्य विकसित मध्य प्रदेश एवं आत्मनिर्भर देश के लिए परंपरागत एवं आधुनिक विज्ञान के लिए पारिस्थितिकी तंत्र का विकास करना है। मध्य प्रदेश विज्ञान सम्मेलन एवं प्रदर्शनी 2021 के विस्तृत कार्यक्रम, पंजीयन और शोध पत्र भेजने के लिए वेबसाइट www.mpvs.in पर सम्मेलन एवं प्रदर्शनी 2021 में सहयोगी बनकर मध्य प्रदेश को एक आत्मनिर्भर प्रदेश बनाने की ओर एक कदम बढ़ाएं। आइए सभी मिलकर एक उन्नत प्रदेश, आत्मनिर्भर देश बनाने के लिए संकल्प लें। जय जवान, जय किसान, जय विज्ञान और इस बार जय अनुसंधान।
Very good morning to one and all. Could somebody please confirm if I'm audible? Professor Preeti, are you able to hear me? Thank you so much, sir. Thank you
Yes,
for
I
the
can.
confirmation. So a very good morning to honorable speakers and all the attendees of the conference. I am Vasundhara Trivedi. On the behalf of MPVS 2021 and NSDCS Lab IIT Indore, I welcome you all to the Conclave on Fabless and Fab Semiconductor Ecosystem being organized by Madhya Pradesh Vigyan Sammelan and Expo, MPVS 2021. It is my pleasure to invite Professor Preeti Ranjan Panda, Professor CSE IIT Delhi, for the first keynote talk. Professor Preeti Ranjan Panda received his BTech degree in Computer Science and Engineering from IIT Madras and his MS and PhD degrees from the University of California, Irvine. He is currently a professor in the CSE department at IIT Delhi. He has previously worked at Texas Instruments, Bangalore, Synopsys, Mountain View, and has been a visiting scholar at Stanford University. His research interests include embedded systems, design automation, memory systems, and energy efficient computing. He is the author of 2 books, Memory Issues in Embedded Systems on Chip, Optimization and Exploration, and Power Efficient System Design. He is a recipient of an IBM Faculty Award and IESA Techno Mentor Awards. His research works have received Best Paper nominations, Codis ISS, and Most Downloaded Paper of ACM 2 Days Journal. Professor Panda currently serves as the editor-chief of IEEE Embedded Systems. He has served in the editorial board of IEEE TCAD, ACM, TOCAS, and Springer IJPP. I cordially invite Professor Panda for delivering his talk. Over to you, sir. Professor Panda, are you able to hear me? Could you please confirm?
Yes. Shall I share the screen?
Sure, sir. Sure.
Is it fine?
Yes, sir.
Okay. Thank you for this opportunity. I realize it's an exciting time in semiconductors for everybody, and it's my pleasure to discuss a little bit some of the applications of things that are coming up with newer opportunities in the semiconductor ecosystem. And the topics that I have planned to cover today essentially are around higher levels of design abstraction. So what happens when you have the technologies available to us on the semiconductor side? How do you actually put these things together and deliver a chip that works in terms of performance and power and so on? The ecosystem is a complicated one. It starts with the technology, with the fabrication opportunities, which we all know are coming up in a big way. But I just want to emphasize that it doesn't end there. There is a lot else that is part of the picture and that makes up the semiconductor ecosystem. So that's what the discussion will be about today. Feel free to ask questions at a time of your convenience. So we'll try to make it short enough that there is enough time for discussion after the presentation also. Okay, so what does this ecosystem consist of? First of all, there are the devices, and following up from there are the circuits that form the building blocks. When the technology evolves, these are typically the first lowest levels of abstraction that receive some attention and innovation along this axis. What next? There is a huge amount of design automation that encapsulates these devices, the new devices, newer generation devices that are available, puts these circuits together that people have built for us to build a larger system with it. So it's an important bridging of the gap technology. This is all these are all software tools that allow this important bridging from these immense capabilities that the devices, the fabrication ecosystem have created, to all the way to being able to put them in a system, put them together in a system that achieves some functionality. So we'll talk a little bit more about what's involved in the design automation. Somewhere along at a higher level of abstraction would be the creation of system on a chip and the system level design associated problems, all the way up to applications and software that just treat all of this as a black box, as a device that is just delivering some kind of functionality for us to then build complex systems in software with it. So the important things that we'll discuss, pay some attention to today, are these two intermediate layers. So somehow the device part of it somehow is understood as falling in a natural, within the natural scope of the semiconductor ecosystem. The applications and software part of it often completely ignores the underlying details of what's there in it. But these other two intermediate layers are what we can talk about today, because some of that is not as well understood. This is a part of a black box that the applications engineer writes software for. What is underlying that might not be appreciated. Similarly, from the device engineer side, from the other point of view, the transistors are created, but the rest of it is not the transistor designer's business, but somebody's business it is to fill these these gaps consisting of the green oval and purple oval. It is a huge functionality, often not appreciated to the extent that it needs. So that's where we'll be discussing some examples of first define what is involved in these technologies, and I'll continue with at the system level design side some specific research problems that arise in this context. Something that is exciting. There are many people already working on these things, and I just would like to emphasize that some of these newer technologies, they might seem a little into the future. These are not things that are available in the market today. It is not something that we can easily build things with, but then that is where the research kicks in, where there is important research that can be done within the research ecosystem. You don't really need that device to be present because these are futuristic systems that questions are going to be asked, right? But then we know that if we are going to invest along the semiconductor path, then it is the responsibility of the researchers to evaluate what is the consequence of various new technologies, newer devices that are coming up, and present the case for whether good, if you replace the technology, then what are the implications? Those are the responsibilities of the design automation researcher and the system level design researcher. So that is the overall context. some of these things actually have an important impact on curriculum. Some of that is not too appreciated these days. The fact that there is a big skill gap that exists among design engineers, electronics engineers that we as academic institutions put out into the market. The reality is that most of the jobs are there in the digital design domain just because of the complexity of these huge billions of gates designs that are being designed out there in the market today. Some of the appreciation of that hopefully will come out through this talk. But this is not hidden in any way. If you just look at the job descriptions of all the companies that are being put out, that's very clear that different aspects of the digital domain, digital design domain, just because it is such a complex and challenging task. That's where all the investment is. That's where all the jobs are. That's where literacy is expected in the engineers that are graduating from the college. Yet, the primary academic focus is pretty is relegated to a pretty small part of it, which is just the analog part and the circuits and the devices, which in that overall hierarchy is the lowest level of abstraction. The importance is not, of course, being challenged, but in fact that leaves a huge gap with respect to what after that. Much of that our engineers are not really very familiar with as they graduate from college, but then they have to go through an extensive industry training, pretty much starting from scratch regarding what is involved in that. So the gap is most definitely there. It has been felt in the market for a long time now. With all this additional investment into the semiconductor ecosystem, something for institutions to also, us as academics to also reflect on what kind of enhancements are necessary. So let me go ahead with making the case of these two: design automation, system level design, these being the bridging technologies that take us from the circuit side from the circuit side of things all the way to an application and a software side of things, where all the technological abilities that are there in the that the fabrication facility is making available to us ultimately is delivered as technology that somebody can use, somebody can analyze, and so on. So with that, let's take a look at what are these design automation tasks that we are talking about. You could think of these as roughly being divided into some high level categories. This design, when I say design here, it is just some higher level design, gate and multiplexers and arithmetic components and so on. So this design and implementation consists of various synthesis technologies, logic, RTL, high level. You can keep going higher in the level of abstraction at which you decide, at which you specify things, and automation paths are necessary to start from those levels and go down all the way to the gates and the transistors that we are then assured of behaving in a certain way because of the technological advance. So that's just one of the things which is taking a specification at whatever level of abstraction all the way down to an implementation, which is a circuit implementation at the end. So all of that we may club together into a design and an implementation. What next? There is a verification that goes on. Every time you design something here, there is the associated simulation, emulation, formal verification, post-silicon validation, finally testing and test generation. This actually is also an equally complex set of tools. They might appear to be tools to the user, but Of course, anybody who has used these things know that there is a huge amount of creativity and innovation that goes into proper working of a verification tool. So some of these problems are actually even theoretically very difficult to solve. Formal verification is one of them. How do you know that what you started off with is actually equivalent is actually implemented by whatever it is that is generated after all this set of design steps? So that's just one of the questions. These technologies are also very fascinating. Post-silicon validation refers to taking out some lab samples of the chips that we are designing, and then trying to do verification with them in a way that would be much faster than our simulation typically delivers, because this is a real system that we have. Even after we have them, there is this matter of testing. All of them are okay or not. If some of them are not okay, we should discard them, not take them to further packaging and so on. But how do you do that in an efficient way? That's this set of tools here. I can go down further. Physical design consisting of placement, routing, checking of various kinds. All of these together form this large and complex design automation ecosystem. This is just, of course, subset of the things that are happening. But this is where there is a lot of the design automation is actually happening. You start off with what seems like an HDL description, hardware description in a very abstract way, which just looks like a language, looks like a programming language specification. But at the end of it, you have a transistor implementation. And what are these steps that we go through to reach there? And each of these steps, how do we actually verify that it's doing the task it is supposed to do? It's a pretty complex set of steps. There are hundreds of sub-steps that are involved in these. And if I were to put them all together in one slide, it might look something like this. What are the careabouts here? There are various things that need to be optimized. Classically, there is this area of the design, there is the performance. Increasingly, power and energy show up as metrics that we want to optimize, but it doesn't end there. As we speak, there are other concerns that come up, and designs need to be evaluated along these different new axes. Maybe it's security, reliability. So some design that you create falls somewhere along all of these axes. These are not just two-dimensional, there are several dimensions there. But a particular design that you come up with falls somewhere there. How good is it? How does it compare with some other possible designs, possible candidates? That is essentially the design automation problem, right? At the end of these, automation is heavily necessary to go through this task and tell us at the end that these are the candidate solutions among all the ones that are. So that's the scope of the problem. This offers a uniquely interdisciplinary opportunities. The subject at the end, of course, involves a lot of electronics and physics, because these are delay problems, power problems. Performance is a delay problem, right? Ultimately, these are the time required to charge and discharge of a capacitor and so on. These are the things that ultimately determine our performance. Area, cost, cost, area translates into something like a cost, and all of these things seem to be very physical in nature because these are transistor circuits that are involved. But the moment you have millions or billions of transistors and gates, there is clearly the need for a lot of automatic analysis. These are not manual decisions to be taken by a designer, but a heavy automation is involved. And when all of these simultaneous criteria for optimization exist, then of course, this has to be done algorithmically. So that's where a lot of computer science aspect feeds into this kind of analysis, making it a very nicely interdisciplinary topic. Sometimes we ignore technologies like this that are obviously important in some sense, to make sense out of the billions of transistors that the technology gives us. But then it's also interdisciplinary. I mean, so it's normally not so easy to find people with expertise in both. So in both of these areas, on the physical side of things, electronics on one side, and the computer science side of things. From the computer science point of view, it might appear to be just an application, it's like any other application. From the electronic side of things, it might look like, hey, there is not much circuit design to be done here, so it's not our problem. So often interdisciplinary problems face these kind of challenges, which of course in some way is impacting what I pointed out early on, that that industry has this big need in terms of exposure of the engineers that join the industry, but yet there are some gaps in academia which lead to a less than optimal output in terms of the background. The topic itself, design automation and the associated technologies that I'll talk about. These fortunately continue to be relevant. The technologies have changed dramatically over the years, yet the design automation problems interestingly continue to be relevant, because these new challenges come up and the technology evolves. This is not evolution in some natural way or in some very predictable way. We have seen that with the shrinking of the transistors. First of all, there is that shrinking leads to lower area and so on. Yet it's not obvious. The technologies people are talking about today have very different characteristics. For example, in terms of power and energy, these things are dramatically changing, because of which the older because of which the optimizations the tools would perform in the older technologies many times become quite irrelevant in the newer technologies. So much of it has to be redone and redesigned and re-engineered. So challenges continue to exist there, which makes this the overall field itself very exciting. That's why the tasks here, while logically they remain the same, the details become very, very different, because the technology means now the way you place them might be different. The kinds of design rules that you would check would be different. The kind of optimization that you would do higher up in your design and implementation phase, those would be different when the technologies change. We'll look at examples of that right now, but this just could be like a one-slide summary of what's involved, what are the challenges involved in the design automation, and also the challenges on the academic side, not just with respect to research, but also with respect to teaching and training, because this kind of a gap in the curriculum has been there for quite some time. Or maybe it is an opportunity to do something. Higher levels than the design automation, we can move to the system level, where, of course, we would be using those the smaller blocks that we designed, and now they become the building blocks, and we are building even larger systems on chip. So what are we talking about here? The building blocks become larger. They are not gates, they are not transistors, they are not flip-flops and registers, but in fact, they might be processor cores, they are caches, they are networks, memories, and so on. So much bigger blocks for us. So obviously the same algorithm, same techniques that we would use to optimize in logic synthesis wouldn't be applicable here. We have to conceive of new problems, new optimization problems, and associated solutions. What's involved here? What you see looks like pretty much what a processor might look like here, right? So you have some CPU core, L1, L2 cache, last level cache, interconnect. So this looks like a typical processor design, but in fact, that's just only logically speaking. But what has happened is there are many of these components that are application specific. They are customized for a function called accelerators, which actually completely throw out the system. It doesn't, even though logically it might look like, yes, there is processor here, cache here, and so on. Familiar things from the architecture point of view. But in fact, the specialization of that system on chip really in these parts that are customized. The other ones might just be some standard blocks that you put there. They are understood components, not much to design there. But the design focus is here in these accelerators that are custom. So those are there. When this come up, though, that leads to a very interesting new set of design automation problems. We typically don't call them design automation anymore. So somehow the level of abstraction has risen. It's higher now. So that's where the system level design comes in. The kind of questions you want to ask are, they correspondingly deal with the larger components that we have here. It might be like hardware software co-design, right? So there is the part of your application is going into hardware. There is a part that is going into software here running on the processor cores. And what is a good partitioning of our tasks? How do we orchestrate our tasks? Some of them running on this CPU cores, but the heart of it may be running in accelerators. And how do we make sure that this is properly coordinated? There are policy decisions everywhere. Even though you take what are regular cores, there are choices among the processor code. There are choices to be made of the cache sizes. There are choices to be made regarding policies and control. How do you allocate maybe cache space, maybe bandwidth, maybe interconnect priority? All of these are intricate problems that show up in this space and that are important system level design problem. So these one can think of the next level. So we talked about two levels that were there, shells around the circuits. One was the EDA, the design automation, which is a little lower level of abstraction. And then we talk about system level design, which is the higher level of abstraction before exposing things to the application software. Okay, so these are the overall context. And what are our research opportunities, development opportunities? Remember, much of this can be done even if we are not fabricating, even if fabrication is elsewhere. All of these support ecosystem is sort of an important thing that on which one can deliver, one can perform that research in spite of not necessarily having access to the fabrication. We talked about this fabless ecosystem, right? Much of the design, of course, is done in software using software tools and can be done anywhere as long as we have put together the requisite set of tools. Research also works exactly in the same way. When the technology evolves, innovation is there everywhere along the VLSI path, where you have design tools, specification synthesis, analysis tools, verification tools, system level design. All of these very nicely actually comes together in the research ecosystem, because usually there would be tools, there would be some access to the tools of the industry, but also there are a lot of things in the open source that we would typically like to put together and make important research advances there. All of that can eminently be done without necessarily investing a lot of resources and money on tools or on fabrication and so on. That is really the most important thing that I would like to emphasize in a presentation like this. Some of these, for example, the technologies that I'll talk about today, the rest of the talk, they seem like very sophisticated designs. In fact, some of them are not even there in the market. They're exploratory. Yet, the research regarding it, how good it is, if such facilities were there, then how good a system I can design. Those are eminently doable, even though the technology itself might not be currently present. And in fact, it's a necessary, it is not an optional thing. You have to perform that kind of research just to satisfy ourselves, for designers to satisfy themselves that in fact the technology is leading to the kind of improvement that we're hoping. Okay, so one example that I'd like to just focus a little bit on is this idea of 3D chip stacking. This essentially is a vertical growth in the emerging technologies. That's an exciting area from a processing point of view, from a fabrication and device point of view. This is very exciting. This allows for a lot of benefits with respect to compactness of our designs and bandwidth that you can expect out of memories and so on. Lots of things are happening there, but the moment that kind of advance happens, there is the opportunity for exploiting it in some way in a system level design, right? It's not enough for that, for the facility to be available in a raw form. Finally, all the way to my application and software and all of those should be able to exploit those opportunities. So we'll talk a little, so that bridging falls in the system level design space, and we'll talk a little bit about the kind of things that can be done here. We have been investigating this for some time. We have put together some tools that are there in the open source, and that's something that maybe I can just discuss a little bit. The specific example of a 3D stacking, which is already there in the market, is the idea of a stacked DRAM, right? So you have this DRAM dice, and through what are called through silicon vias, TSVs interconnection, you just stack them. So these are the layers that are stacked. And why would you do that? Well, compactness is one thing, but in the context of memory, the bandwidth that you are able to get from the system is higher, the latency is lower. So there are lots of advantages there. For now, there is a disadvantage that the cost is higher, but these things tend to evolve over time. But there are some powerful advantages. But the question then is, what do I do about it? Like I said, it's already there in the industry through these HBM and HMC protocols. Many of the modern manufacturers are creating those devices, and they are being used in various kinds of devices, server systems, accelerator systems, even FPGAs. You could think of stacking in very different ways. You could put the CPU next to each other. You could stack the CPU along with the memory. You could actually have multiple layers of CPU along. All of these are being investigated in the research ecosystem, definitely. In the commercial space, at least partially it is there. The DRAM stacking certainly is already there, but putting them together is a possibility. Multiple layers of CPU with DRAM. Some of these are still in the research domain, really. Nevertheless, these are important opportunities for the system level design engineer and a researcher to come up with interesting design problems, all the way to software, data manipulation problems. All of these show up when you have technologies like this. So actually, it's a very interesting time to check out some of these new technologies to understand their implications at the system level. One interesting topic that is of some interest to us, and we have investigated that in some detail in recent times, is the idea of thermal awareness. You have this stacked memory. There's the printed circuit board on one side, and you have a heat sink at the top. So the question is, there is a thermal awareness that's necessary because the heat dissipation is not as good. It's not uniform. It is much worse towards this part than towards the higher part where that is next to the heat sink. Okay, so the problem is that the system needs to stall if that temperature exceeds some kind of threshold. And therefore, as a system designer, you need to be aware of it. So what's happening here, as the memory gets accessed, you see that the temperature rises in a differential way. The lower layers actually get hotter, And some interesting effects are seen. Vertically, there is a gradient. Even horizontally within a layer, there is a gradient because the central channels become hot. What to do about it is really a data manipulation problem and a system level design problem, not merely an electronics problem at the lowest level, because you could do a lot of things. You could back up data to outside to some backup 2D memory, and maybe make sure that the channels are cooler by turning them off. So for you turn power off to those channels. So such things you can do. Then the channel gets turned off. That way there is some cooling, and then you are able to reuse the device again. You could continue this. What happens eventually is that the system is still working, so the performance is not as good, but still it is not completely stalled. The next thing that you can do, you observe, is that maybe because the central part of it is cooler, the adjacent channels are now they are cooler, but the corner ones remain hot. Then I can continue this. So in terms of a policy, I need to come up with some management technique where I back up data to my memory, to the background memory, as it were, and make sure that we are able to derive some benefit from a system like this, rather than the default system where I just install the whole thing until it becomes cool enough that I can reuse again. So you can see things like these allow us the opportunity to optimize the system performance in some very remarkable ways, much more than just the default thing of shutting the system down, which often we see in our systems, in our both the server systems and all the way to the mobiles. Sometimes if they become too hot, everything stops working. That is, of course, an implication of things like this happening. And I just want to point out that in addition to all these management problems that show up as some nice interdisciplinary problems, there are elements of computer science there, there are elements of electronics there. Very interesting high-level policies one needs to think about for how to manage a complex system like that. And one of the things I would like to point out is even to evaluate that system. See, such systems might not be fabricated yet, right? Because some of these are experimental, and the particular configuration that we want to study might not even be there in the market yet. So there is a need to set up in a simulation environment the configuration of the kind that we want to study, and run some applications and check out what is happening, for example, in terms of the temperature gradient. And therefore, that tells us something about the power optimizations that we want to do, the data manipulation that we want to do. All of these decisions need to be taken, but some integrated simulation and visualization tool is necessary. That's the one that I'm pointing out here. We've spent some time in recent years to build such a tool that integrates various other open source technologies, CPU simulator, a thermal simulator, a memory modeling tool, a CPU area performance and power modeling tool, and all the way to a task scheduler that is able to that recognizes what's happening and is able to take some high-level decisions like scheduling of tasks when you're working with the system. So that's an example visualization. What it is showing is that there is a layer of CPU core stacked with some layers of memory. There is that gradient that we had talked about earlier, because at one end maybe there is a heat sink, there is better dissipation, and the other it's not so good. So if you look at the core layer here, the bottom layer, there is a difference based on what each of the processor cores is doing, and based on that you see some gradient of memory layers that are stacked on top. So some nice visualization, and the output is actually a video. I'm not showing that output, but it's an example. That animation that we showed earlier is an example of what that video presents as an output. So such things can be some very nice analysis tools for a system design engineer, where somebody might want to study the impact of this particular policy or some particular power optimization mechanism. Yeah, what are the kinds of things you can do? You can analyze the temperature profile um, of the of this entire structure, 3D CPU and the memory structures. You can experiment with various policies, thermal management policies, task scheduling policies, voltage and frequency scaling, memory power state. So all of these are complex systems. Each subsystem can be controlled in some different way. Obviously, it is an evolving thing, but yes, I do want to highlight that at least the first version of what is there, it was a multi-institutional effort. It involved our group, but there are also participants from University of Amsterdam and Karlsruhe Institute of Technology. It is a putting together of various tools, all of which were also open source, but a lot more was done just to make sure that various configurations that we want to study um, would would be accessible. And yes, that's the link out there. And there was a comment from Kunal. Thanks. Indeed, these are we see them as important mechanisms, tools that could be used to jumpstart a lot of system level design work. So yes, absolutely feel free to um, to play with it, and feedback is welcome. Also, contributions are welcome to enhance tools like these so that the entire community benefits from this. So anyway, let me summarize. I tried first to just discuss the overall ecosystem um, that's involved in semiconductor. Sometimes some of that is not necessarily very visible other than those working in the field. But as there are technological advances in the fabrication space, these are all accompanied by a significant amount of design automation and system level design mechanisms, methods, methodologies. They form a key role in supporting a semiconductor ecosystem. Some curriculum gaps I had pointed out. Of course, this should also be seen with research opportunities that are there. A lot of the research, even though these devices may not be available, that really does not stop us from continuing with the implications, right? Because a lot of this can be set up with open source. So forget about the tools from the market. They may or may not be there, but in fact, the research community is very interested in the system implications. When these new technologies are there, when there is non-volatile memory, when there is 3D stacking, there are lots of activity at the device level, and how that translates to larger system is something that's a very active community that the system level design community addresses. And yes, these opportunities are most definitely there. Much of it is accessible to all of us. It is not that, so that the tool chain that I mentioned, in fact, it's completely based on open source tools. We took open source tools, we have contributed to that, we extended them in various ways, and we have put them back in the open source. So it is an important um, um, set of resources that are there. People are most welcome to not just use them, but also join that community and contribute. So we talked about a particular opportunity here with respect to 3D stacking. It's an emerging technology. Very important new advances are being made with respect to higher performance and compactness, but also very critical challenges remain with respect to how you manage the temperature gradients and thermal issues, and how at a very high level, right? At the lowest level, there is some management that can be done, but it's that management tends to get exposed to at the highest levels what kind of control that you can do. And some of these are data problems and operating system management problems. So hopefully some appreciation was there through this talk of both the wider ecosystem and also the specific opportunities that show up when we make advances in the semiconductor. So let me stop here. This is just a list of people from our research group here, PhD students who have contributed to various aspects of the work that I talked about, and also other things, interesting areas that we have been looking at in the area. So the topics being some thing in the cache management space, emerging memory technologies. I briefly talked about that. Accelerators for all kinds of applications and design automation in general. Let me stop here, thanking the organizers once again for inviting me to speak here, and I'll be happy to interact.
Thank you very much, sir.
With questions. Yeah.
Sure. Thank you very much, sir. Any questions from the audience end? You may paste your questions in the chat box if there is any. Okay, sir. I think as of now, we don't have any questions. Thank you very much, sir, for such an interesting session. You have walked us through various aspects of memory design. Thanks for explaining the concepts in so much depth. Thank you very much, sir.
Thank you very much.
So with this, we will move to the next segment, the next keynote talk. I would like to invite Mr. Shiv Kumar for the next keynote talk. Mr. Shiv Kumar is the Chief Technology Officer at the Sahasra Semiconductors Private Limited, which is India's first memory IC packaging and testing company in Bhiwadi, Rajasthan. He is the founder and CEO of Snartech Private Limited, which focuses on AI technology. He is an expert in IC packaging, wire bonding, wafer level, 2.5D, 3D interposer, etc., with more than 12 years of experience in process, quality, reliability, program management, research and development, and market research and analysis. He's worked in SanDisk, Shanghai, China, and Semtech China, and also in USA. I'm honored to invite Mr. Shiv Kumar to deliver his talk. Over to you, sir.
Hello.
Yes, sir.
Oh, okay. So thank you for giving me this opportunity. And a lot of things are happening in semiconductors since last 2 years. Once we have that Corona and some conflict between US and China, right? So everybody is thinking now, right? How can we be Atmanirbhar, right? In ourselves, so we can use our own made product, right? So last week government released some incentives, right, for making India Atmanirbhar, and their goal is very much clear, right? They want to see the product which have a logo made in India, right, after 25 years, because it's a long phase we need to pass through. That's why they have set up this 1 quarter phase, right, for everybody to work on and then make India Atmanirbhar. So I will discuss about about the overall framework, right, on the manufacturing or processing side, not on the design side, because we already have so many good designers in India and they are doing a lot of things around. So now it's a time to do something in manufacturing side, right? So I'll share my presentation, and I have only 1 or 2 page, not more than that, but so is it visible or?
Yes, sir, it's visible.
Okay, so when we see any product, either it's a phone, laptop, or anything else, so it passes through 4 different steps, right? The 4 different steps, right? So this we see on the right side, it's some charger, right? I have attached the photo here. So this is the end product. In the end product, we use a lot of component that is called packaging and testing of the component, right? And these component goes to the end product. These components are made out of fabrication steps that is done on the raw wafer, right? We see on the extreme left corner, right? So these are the key 4 processes we see. So if we see end product, we are doing a lot of assembly here in India. You know, the Samsung is doing it for mobile phones or for their tablets. Apple is also doing right in Foxconn site in Chennai. And there are still some lack, right, in the end product, like high density PCBs. We cannot manufacture here in India. We're still on the low density manufacture, or quality and reliability for our PCB manufacturing is not too good, right? But I won't focus in this section. My focus will be on the 3 steps, right, which are highlighted in yellow, because that is what government is thinking to bring in India now. Right? So if we see from the step 1, where we have the sand. Why I'm saying sand? Because 90 to 95% circuit are made on silicon. Right? A lot of material are coming into picture nowadays, like GaN devices, gallium arsenide devices. They are also developed somehow on the silicon wafer or some other wafer also, but 95% is silicon. So this process is, so when we move, from end product to the packaging and testing, and then fabrication, and then wafer manufacturing, they becomes more complicated, more cost effective, more sensitive. There is a more risk involved. And why it is? The basic thing is the scale, because when we move to packaging and fabrication and wafer level, the scale of work, the scale at which we work, right, it reduces. For example, like my packaging and testing, that happen at micro level, fabrication that happen at nanometer level, wafer manufacturing at atomic level. And for all these 3 steps, we need highly skilled manpower that can handle very, matured and automatic tools that can handle this process. That's why we are still waiting for all these 3 processes to be happen in India. And another thing is, the huge investment that is required to set up any of these processes in India, right? So this is, we say, a complete product chain, right? This is a chain of a product, and how can we build the ecosystem? So in the ecosystem, there are a lot of things which we required for each process. Let's say for packaging and testing, we need equipment, right? So equipment manufacturers should be here. Then you can reduce the cost. If they are not here, they are sitting somewhere, outside India, then it's very tough to handle the process equipments. Substrate manufacturer, and substrate manufacturer, raw material manufacturer, like we use a lot of metals for conductions, right? Adhesives, tapes, mold compound, gold wires, or bowls, right? Chemical manufacturing units. So in chemical manufacturing units, we use a lot of gases, right? And those are your very high quality gases. And the consumables which are used, to carry the material inside the factory or outside the factory, right? So until we have all these setups here, it's going to be very tough for us, and we need to build this ecosystem. We need to bring all those guys who are already market leader in this sector somehow to bring in India, uh, in parallel with this packaging, testing, fabrication, or wafer manufacturing unit, right? And that gives a lot of opportunity for us, because they will generate a lot of jobs, right? Then the second main concern is a government support, because for all these 3 steps we need 24/7 electricity, uninterrupted pure water. We need to build the good clusters, and the transportation system should be very good. Incentives which government has released last week, and we need to see whether they are enough or not, or we should discuss with government, yeah, more on that front. Why I'm saying for the incentives from government? Because once you input huge amount of money in any of these process, we need to wait for 2 to 3 years, which is my the last point here. Huge upfront investment, and it takes at least 2 to 3 years to start something. Either it's a feasibility study, characterization, and then you build your product, show it to the and customer users. They will do their qualification. That is also 3 to 6 month process. So it's a long chain. So this investment guy, he need to be have a patience. And again, the skilled manpower in terms of process, right? So which we don't have at this time. And if you see more than 25% or Indians outside India, right? They are building these chips, right, from their hand. So we have the expert people, but we need to create that things in India, and that will also take some time. So these processes are very complicated processes. So now my next page is on the investment side. What is the key here? The investor and the technical team both are the key person in this overall scenario, because once if I go back and if I talk about the packaging and testing, right, that takes around 200 to 300 crore rupees investment. That is upfront cost, and then you wait for 2 to 3 years for fabrication. Depending on the application, it's from $200 million to $10 billion. So this much of investment, if somebody is putting, right, he should have a patience, and he should have belief in their technical team. The same is true for wafer manufacturing. So it's a combination of both, good investor versus good technical team. If this combination breaks down, then we cannot catch this opportunity which is available now in India, right? And once they are good and they capture this opportunity and they have the long-term relationship, they can go ahead, and it will be good for long term, right? For both, either it's a technical team or investor team, right? So in the semiconductor, we should take care of each other, right? Investor should take care of technical team, and technical team should take care of investor also. So this is the basic fundamental we should think now, right? Government has already released whatever they wanted to do. Now it's a combination of these two key person, right? Technical team we need to find out, because we don't have so much technical expertise in processing side, right, in India. So next is, if we see just a little bit about the process flows, right? What we do in each of these steps, right? As I mentioned, I won't discuss about the module because this is something what we are doing right now, right? So packaging and testing, the first thing is we get the wafer, right? Wafer sorting is done, and then we do grinding and dicing. That is based on what is the form factor of the chip, right? And it's very critical and complicated process itself. Then die bonding and die attach, where the material analysis of each layer is the key, right, for process engineer. Then we do the wire bonding. Again, the wire bonding material, how will it join with the pad? This kind of analysis is very critical, because everything is happening at micrometer level. If we see NAND flash memory bonding pad, generally it's 50 micron by 50 micron, and the pitch is around 60 or 65 micron, even though it's decreasing nowadays. So we need to see everything in that small scale and then make it happen. Then of course encapsulation, laser marking, source simulation, test and chip. So it's a big opportunity that is coming in India, and we hope that we can do, right. In Sasra, we are starting doing the packaging for the memory that will be first of itself in India. The wafer fabrication, I think most of the guys should understand, like layer deposition, oxidation, photolithography. These are the steps, right? And it involves huge investment. If you have heard about the news, 1 month before, ASML built a machine that can do 2 to 7 nanometer lithography process. That is $140 million tool, right? And they have spent around $3 billion to build that tool. It was with the collaboration of Samsung, Intel, TSMC, and there is one more company. Wafer manufacturing, This is also, because here everything you need to do at crystal level, right? It should be very clean, and the lattice mismatch and all those things matter is a lot, right? Again, based on the applications, right? So these are the things we need to focus once we go and do the backward integration. Pandaji were giving talk about the design, right? So just one more point here, what is the basic difference between design and the process, right? Once you do the design or you do the simulation, you do it in real condition. Of course, you give some tolerance, right? But when you try to build it physically, the condition changes every millisecond. Stress you are putting on your devices, it changes every millisecond. That's why it takes 3 years or 4 years to build a product, right? Really build a product. So this is what I wanted to, show you guys, like how can we do it, and what challenges are here, and what we need, from the government, and how can we do it. Hello.
Thank you very much, sir. Sir, are you able to hear me?
Yes, yes, yes.
Yes, okay, sir. So anything more you want to add, sir?
No, this is, what I wanted to show you guys, right? How
Okay,
can
sir.
we move to the manufacturing now, from design to manufacturing?
All right, sir. So any questions from the audience end? Sir, there is something in the chat box from Mr. Kunal Ghosh from VSD. You may refer to the comments. There's no question as such, but there's just communication. Any more questions from the audience end? I request everybody to put their questions in the chat panel in case. So I guess, sir, there are no questions from the audience end.
Okay. Okay. Thank you guys, for inviting me again.
Thank you very much, sir. This was a short but an effective presentation about IC fabrication, and it was really an interesting talk. So we're really thankful to you for joining us on MPBS 2021. Now we'll stop for a lunch break, and I would like to ask all the participants and attendees to join us at 2 p.m. for another keynote talk, followed by poster presentations. So stay tuned, and thank you very much.